Hey guys, welcome to day 10. This is going to be our first steps into what encourages actual calculus. Now, before this, we were just talking about some of the big ideas that are really prevalent, kind of how to do the manual labor. This is sort of like your workout before you show up to like football practice or basketball practice. Like you have to be in shape mentally before you go into an advanced setting like calculus. You you need to know some basics and be fully comfortable recognizing those basics and how they're used before going any farther. Now, for today, I'm going to be hitting on some pretty little topics, discussing some unique approaches to some abstract math. It'll be a lot of talking. At the end of the day, you're going to have only a couple of problems, not very many, but the idea is going to be to look and see how to connect calculus kind of into the world of mathematics that you've explored so far. And that's a unique concept that really needs to hit home because otherwise calculus feels kind of disconnected from everything else. It uses, of course, the same formats and the same variables and stuff, but without the connective glue to hold everything together, calculus feels like a shot in the dark, like it's off on its own, like it's the no friends, no neighbors, no love. All right? So let's talk a little bit about kind of how calculus fits into everything else and see how we can have that conversation so that we can actually better understand where calculus comes from and how it fits together. First, there are three major aspects of calculus. There is limits, which is the first thing we're going to talk about, and we're going to spend the majority of the rest of our summer. There's differentials, also referred to as derivatives, which is the second major part of calculus, and the largest part of Calc 1 for most students. And the third part deals with what's called integration, or an antiderivative. It's kind of the opposite process. So I want to introduce you to some concepts you've seen before, some topics you might have heard of, and talk about how calculus separates them. Okay, to do this, I'm going to use a little visual aid, which comes from a textbook that I happen to use. I love this textbook. It's a Larson textbook. It's great. Your school may use it too. There are a variety of different ways to talk about this, but this is just one of the ways that I like. Okay, so here's my textbook. It's beautiful. I know. Everybody should have this textbook. It's great. This is a PDF that I have. I was able to find it online. Actually, a student found it for me, which is great. And this kind of shows the connective tissue between pre-calculus topics versus what's happening now. So, first of all, without calculus, there's a lot that you have learned and things that are very important that can drive business practices. It can showcase how to set up various realistic scenarios like with trig and geometry. It can go more abstract and deal with how polynomials interact. You could survive your entire life without needing calculus. But calculus was one of the first major developed mathematics, meaning it was chosen and designed to solve specific problems that were not solvable before. Algebra feels very natural, right? You start with an unknown. Well, if I have an unknown and I add another unknown, I can put those together and it's two unknown, right? Or if I have an unknown and a separate unknown, right, I would want to put one of them as a variable x and the other one as a y, indicating that they are different unknowns but both unknown. And so without calculus, you can do a lot. But calculus fills in a lot of gaps that you may not realize exist. So let's talk about the first one. In mathematics and algebra, you're used to being able to find a value. So being able to take a value like c and plugging it into an equation, which is fantastic, right? It means you can do a basic substitution. That's one of those basic algebraic properties. You can plug in a number and get an answer. Calculus allows you to do what's called a limit, which means that if for some reason you are not able to plug in that value, or that value is not one that when you plug it in gets a result you're expecting, then the limit can determine what value you expect to get, how you should get, based upon information relating to it. Think of it like if you fill up your gas tank. You fill up to a certain amount, you expect to get a certain amount of mileage out of it. If you get something other than the expected value, you start to wonder if something's going wrong. Maybe there's a hole in your tank causing you to get a much lower value than you expect. Maybe for some reason your value is reading incorrectly, and so when you thought it was a full tank, you actually put in more gas than you were expecting, and so you're getting a much higher value out. And so we have expected values in mathematics of I expect to get $5, and sometimes you don't. Maybe you get nothing. Maybe you get $1 million. Not common for sure, right? That'd be great, but it doesn't always match the expected value. And calculus helps to assist with separating the expected from the actual, which is a big distinction. In algebra, you can expect to do things like find slope. That's really common. But you find slope specifically of lines, of how a line is acting. You can determine the slope of a line using a formula, right? We talked about y2 minus y1 over x2 minus x1. That's the basic slope formula. Or delta y over delta x. Well, in calculus, we can assign slopes to curves, meaning we can determine the same properties of that line, like is it increasing, is it decreasing, is it staying constant, is it undefined. We can talk about those as aspects of a piece of a curve, which we can't do without calculus. Right? If we look at this picture over here, we can see that at this dot, it will have a particular slope, because over time, this dot indicates the graph is increasing. It is going up over time. But over here, it would have a slightly different slope. In this case, over in this portion, since the graph is tending downwards, it would have a negative slope. And so when we talk about calculus, we can talk about the ideas of algebra administered in a way that makes sense with non-algebra problems. I can't define slope of a function without calculus, despite slope being a natural thing to look at, right? We can all look at this picture and be like, oh, clearly it starts by going downwards, it then trends upwards until it reaches a maximum, and then it trends back downwards again. We can all see that. So why mathematically couldn't we find those values? That's what calculus does. It says we can actually determine what the change is at any dot on that line. Similarly, how without calculus you can determine things called secant line. Secant line indicates the line in between any 2 points on a curve. Calculus deals with tangent lines, where it says, okay, what's a line that matches the slope precisely at one spot? In physics, you might talk about things like average acceleration or deceleration, or average change or average distance. You deal a lot with average. But instantaneous, like what's happening in this exact moment, that's a calculus question. You cannot solve those with standard physics equations without calculus. And many of the equations you might see in a physics class are derived from calculus, meaning you may not use calculus to get your answer, but calculus was used to get the equation you're now using. Other things like curvatures, right? You can talk about how a curve on a circle is defined using a function, but you can also talk about curvatures of any curve, because this curve acts differently no matter where you're at. Same thing with like heights, right? Physics application again. You'll find a lot of physics applications are in calculus because calculus was designed to answer a lot of physics questions. You can determine a height using a formula. You just plug into the formula and get a solution. But what that formula won't tell you is if that's the max height, if that's the min height, or anything else. All it can tell you is where it is right now. And that's not useful in a lot of settings. If you're doing something like launching a missile or throwing a curveball, you want to know some basic things about, where is it going to start, where is it going to stop, what's happening in between those 2 points. And you don't want to have to sit there and ask what's happening here. Now it's happening here. Now it's happening here. Now it's happening here. Now it's happening here. You don't have to ask 1,000 questions to see the path. You want to be able to ask what's happening overall. And the calculus can do that. It can determine those values for you. Same with things like tangential planes and directions along a line versus directions along a curve. You can determine an immense amount of material using calculus. Similarly, using integral calculus, which is the other half of calculus, You can use geometry to determine the area of a rectangle, or a lot of other shapes, right? They are very common shapes: rectangles, squares, circles, trapezoids, polygons, right? You can find areas of all those shapes using formulas. And while some of those may involve some trig, like, you can do it. But what if the shape isn't a standard shape? Like, what if it's like an amoeba shape, or like a curved shape, like this one here in our picture here? How would we find the area of this pink space? Well, you can't do that without calculus. At its most basic level, it is impossible. You cannot find that area. Now, you can get close, and in some cases, that was enough for a lot of history. But the more advanced you want to go, the more precise you need to be. If you're designing a wagon wheel, you can be off by a centimeter or two and it not really affect how the outcome is going to go in many cases. Certain areas are worse, yes, but it's not that big a deal. If you're building a spacecraft, if you're off by a millimeter, the thing might blow up, or it might fall apart, or it might not take off at all. And so you have to be very, very precise. Close isn't good enough. Similarly, like in physics, you can talk about work done using constant forces. That's a non-calculus topic. You used to work equals force times displacement. But if the amount of force is changing, as is common in almost all physics systems, which is very rare to have a constant force, well, integral calculus can tell you how to find those things. You can use properties to find things like centers of basic shapes. But if you talk about an advanced shape, you can't really do that without integral calculus. If you can't somehow break it down into rectangles or triangles or circles, then you can't do it. But integral calculus can. While you can use a ruler or even some geometry to determine how to find the length of a segment, right? You use the Pythagorean theorem. You can find that length just fine. But what if it's a curve? How do you find this length? Well, it turns out you can. It just takes calculus. It just takes a different type of looking at the problem. You can do things like surface areas, volumes, which is related to mass, densities, and you can sum together infinite pieces as opposed to finite pieces. Calculus is designed to fix a lot of these gaps that, again, the average person may not need to do this, right? The average person doesn't need calculus in their day-to-day life. But I hope you're taking this class because you want to go into mathematics in some way. Maybe you want to go into an engineering field or a science field. And math is a form of science. It's a language in which many sciences are based. And so understanding calculus is the first step to understand deeper sciences. And I hope that's why you're in this class. Now, for us, we're now going to look at something referred to as the tangent problem, which deals with slopes, which will be kind of where we start a lot of our limit problems, as well as the area problem, which, again, both of them are designed to fit into calculus, right? The area problem is fit in here. The tangential problem fits in here and here, these three. Whew, sleepy. So we're going to talk about how we talk about these subjects with calculus in a way that hopefully starts to build off previous material into more advanced material that has all these different topics. So we can set aside all these major pieces of non-mathematics and see how to understand and better determine which pieces actually fit together, so we can actually do the fundamental parts of calculus. We are going to answer throughout your calculus classes, either with me or without me, a number of fundamental questions that don't exist in other classes because they can't exist in those classes. And hopefully, by the time you're done, you have a better appreciation for what some of this math can do. So, let's get started. Okay, so let's talk about our first major piece. And this is referred to as the tangent problem. If I have something like a curve, like so, and I asked you about the slope of this curve. Okay? When I ask a question like that, it's entirely dependent upon one major thing: where I'm at on the curve. If I pick a point like here, this point would have a slope that is a slope of 0. Because at that point, to the left of that point, you can see how it's going down over time. To the right of that point, you can see how it's going up over time. And so in between those two, there has to be a 0 value. If I picked this point instead, you can see that the slope will be represented by this blue line. This blue line would indicate how the function is changing over time. Because you can see that at that blue dot, like to the left of it and to the right of it, are both going up over time, and so this dot is also going up over time. But notice how we can't determine what's happening there because it's not a line. We can only determine slopes of lines. Furthermore, if I was to continue and choose a different point again, let's say over here, you again get a slightly different line which has slightly different slopes. And so at any of these three places we can talk about slope. We can talk about how the function is changing. Is it increasing? Is it decreasing? Is it doing nothing? Is it undefined? We can have these conversations like you would in an algebra class. But when you look at the curve, it becomes very difficult on how to do that. And so this is where we start to see how some of the first calculus was created. And so what the first calculus said was, hey, on that curve, what if I pick 2 points that are near? And what they mean by near is they mean picking values where they end up being very close together. So for example, if I want to find this red dot, what if I picked a dot like right next to it and another one right next to it? What if I picked these two spots on the graph? Would those get me close? That seems like a weird thing in mathematics, that because in math we're used to getting an answer, right? We're used to getting, 7, 2/3, pi over 6, right? We're used to getting hard, concrete values. But in calculus, we start to say, well, maybe the hard, concrete value comes later. Maybe it comes from actually getting an understanding of how these pieces are supposed to fit. And so calculus said, okay, if I take any curve, in this case, I know it looks like a straight line, but let's assume it's got a curve to it. If I want to determine what's happening here, at that dot, one of the things I can do, let's call this dot A. So A is going to have two values. It's going to have an X value, so X sub A, and a Y value, Y sub A. What it says is, hey, what if we pick a value that's close to it? We're going to call that value B. Well, we could get an approximation for the slope of this number using these 2 points. We could do delta y over delta x using this b's value, so x sub b, y sub b. We could do your basic algebra process where we do y of b minus y of a over x of b minus x of a. And we get close, right? But this leads us to the second part. What if those 2 points got closer? What if instead of choosing B here, what if I chose B right here? Let's call it C. Would these two give me a good answer? Probably. Pretty close, right? But these two would probably give me a better answer. And what if I kept that process going? What if I chose like, a number that was Very close. D. What if I chose a number that was so very close to it that it was almost impossible to tell the difference between those? Well, this concept is referred to as a limit. The idea of a limit is we approach a known value using near values. So for example, if I want to get to, say, 5, I have two ways to do that, right? I could just 5, right? It's a number. I could just plug it in. If I want to determine what f of 5 is, right? I could just plug in 5 and get an answer. But let's say I try that and it doesn't work. Let's say I plug in 5 and I don't get an answer. Maybe the answer is undefined. Maybe for some reason the answer I get isn't what I expect. Well, what the limit says is, well, what if I look at 6? Well, 6 is close to 5, so wouldn't f of 6 be close to f of 5? What if I looked at 5.5, right? That's closer still to 5. So if I want to know what's happening at 5, could I look at 5.5, which is close to it? What if I looked at 5.1? That's even closer still. Is this not going to give me a close answer to where 5 is? And for some functions, yes, it does. Others, it doesn't. So what if I took this process and kept it going? You know, what if I chose like 5.001? Or, you know, let's just keep it simple, 5.01. 5.0001. 5 point with 4 zeros, 1. Would not each one of these get me closer and closer to 5, and therefore get me closer and closer to what this answer should be? Let's look at a very simple problem. In this case, we're going to do x squared minus 1 over x minus 1. Okay. If we look at this equation, and I ask you, what's f of 1? Here's the thing. If you try to plug in 1, you will not get an answer. Plugging in 1 is undefined. But here's the thing. If you try plugging in numbers that are close to 1, you start to notice there's a pattern to your numbers. So for example, if we take this value and use an actual calculator and plug in 1, you would not get an answer. But let's say you plug in, say, f of 2. You will get a number. If you then plug in f of 1.5, you will get another number. F of 1.1, you will get a number. F of 1.01, f of 1.001. Right? Each one of these numbers gets closer and closer to 1 without actually being 1. Let's grab our calculator. Okay, so here's my calculator. Now I'm going to take my calculator. I'm going to type in each of these little equations. First of all, let's verify that f of 1 doesn't work. So I type in, and I'm going to cheat a little bit. I'm going to use a little fancy thing that I can do. I'm going to use, let's see, the top is x squared minus 1. The bottom is x minus 1. Okay. Okay, so I've got my equation typed in. Now what I can do is I can use the little calc command right here. It's in blue. So on my calculator, I just do second calc. And I'm going to determine the value. So we'll first graph it for me. Notice how, despite what the function looks like, this looks like a graph. What happens if I type in 1? If I type in 1, notice how there's no solution. I don't get an answer. But watch what happens as I start getting close to 1. So again, calculate the value at 2, right? Well, at 2, we get an answer of 3. Well, let's now try 1.5. Let's get closer. Calculate the value at 1.5. At 1.5 we get 2.5. Let's now try 1.1. At 1.1 the answer is 2.1. What about 1.01? You might start to notice a pattern here, and that would be very good if you did. But if you don't, keep looking. Oop, I typed in 2.01. Oops. Calc. Make sure you always type in the correct thing, which should be 1.01. Which gives me 2.01 as my solution. That's because I knew that's what I would get. If I type in 1.001, hopefully you see the pattern. Oh, dang it. 1.001. Let's stick with. Okay, let's take a look. Notice how when we typed in these values, at 2 we get a value of 3, at 1.5 we get a value of 2.5, at 1.1 we get a value of 2.1, 1.01, 2.01, 1.001, 2.001. So as we got closer and closer to a value of 1, look at what happened to our numbers. 3, 2.5, 2.1, 2.01, 2.001. Notice we are getting very close to a value of 2. As we get closer and closer to 1 that we're plugging in, our output is getting closer and closer to a value of 2. And it turns out this is the limit. The value at 1 is undefined, but the limit at 1 is 2. That is because the expected value that we should get is 2. This is how we talk about calculus and why it's so different. Because an algebra student can plug in 1 and get undefined and be forced to quit. But a calculus student can go farther and say, well, this undefined value, maybe it's because 1 is a problem. And if we get close to 1, we can kind of see what's happening around it. It turns out if you do this exact same process, this exact same steps, let's say, instead of approaching 1 from above, like we did 2, 1.5, 1.1, these are all values that are bigger than 1. What if we did it from below? So we approach it from, say, 0, and then 0.5, 0.9, 0.99. Each one of these is closer and closer in value to 1, and what you'll find is that over time, each of these also approaches the value of 2. You know, at 0, this function gets a value of 1. At 0.5, this gets a value of 1.5. At 0.9, this is 1.9. At 0.99, 1.99. So you can see how they each end up getting closer and closer to the value of 2, just like these got closer and closer to the value of 2. And thus establishes the idea of a limit. We're looking at how we get close to a value. Now, based on this topic, I'm going to give a short homework assignment, which deals with basics of limits. We're going to go more in depth into limits over the next 2 weeks. This will be different than anything you've talked about in a previous class. So keep an open mind, and I'm more wanting to see what your theories are on your solutions rather than your actual solutions. As long as you do this assignment and write out what you think, you will get full credit. So make sure you take a look and try to guess to see what you think would evaluate the limit of this function. For now, that'll be it. Make sure if you haven't submitted your quiz already, make sure you get that to me as soon as possible. Remember, it is due on Friday at noon, like everything else. Otherwise, that'll be it for today. I look forward to seeing you guys tomorrow, where we continue our topics on limits. Have a nice rest of the day.